Hello, everyone, and welcome to the second lecture of classical harmonic analysis. So before I say or state or do anything else, I want to introduce some terminology that I'll use throughout the rest of this course, and that is this infinite series here that I'm circling, where particularly the coefficients in front of the exponentials are the Fourier coefficients f hat of k. This whole infinite series is going to be called the Fourier series of f of x. So that's regardless of whether it converges or not in any way, shape, or form. That's regardless of whether or not it converges to f of x for any x in any way, shape, or form. Okay. So what I want to talk about for a little bit in this lecture is differentiation of Fourier series. Okay, so as I mentioned, one of the main applications of Fourier series is to differential equations. So it's good to know and to get some properties about derivatives of Fourier series and differentiating Fourier series. Okay, so what I first want to prove is a very general proposition. It's a little bit stringent in practice, so it's more of a very, very general theoretical result. It's probably one of the only general results you can prove. Okay, so let's suppose I have a sequence of complex numbers satisfying this condition for a positive integer n. Okay. So certainly that means these ck's are in the little L1. So by the Weierstrass M test, this infinite series converges absolutely and uniformly for all x. So if I call this function f of x, and I claim that f is n times differentiable, and I can differentiate f by differentiating term-wise this series here. Okay. All right, so in practice, I should mention that this is, as I said, it's a bit stringent. Typically, what you have in practice is that the ck's decay like 1 over k or 1 over k squared. Occasionally, you'll get 1 over k cubed. And 1 over k cubed would allow you to set n equals to 1 here. Because that would be a sum 1 over k squared. That converges. But even if you have decay like k squared, you really can't even set n equals 1 here. So in practice you need. But we'll talk about what to do in practice. But like I said, this is really the only general result you can state. So. And the proof is a nice proof. It's an interesting proof. Okay, so what is the proof? The heart of the matter is n equals 1, right? In general, it's just an easy induction. So let's say big f of x is this infinite series here, which I should say, when n equals 1, if this is true, this sum converges, then again, Weierstrass M test says that big F of x, the sum here defining big F of x is convergent uniformly and absolutely for all x. Okay. So let's look at the difference quotient here, f of x plus h minus f of x over h. Just plop this into the definition of f. And let's use properties of exponentials, and I'm going to factor out an e to the pi I kx. Okay. So let's subtract big F of x and also factor out an e to the pi I kx. Okay. Now, as I mentioned before, we're not often going to be able to just smash in absolute values. So let's enjoy it while we can. And just do that, just throw in absolute values. All right, and this is the sum I need to estimate. And what I'm going to do is I'm going to prove that as h goes to 0, this sum here goes to 0, which will mean that f prime of x is big F of x. And that's exactly what I need to prove. Big F of x is exactly what is the series, the sum I get when I term-wise differentiate little f of x. Okay, so I'm going to use the mean value theorem to get an estimate for this term here, independent of h. So you can either, just apply the mean value theorem to this right here, which is obviously quicker, or if you don't want to, you could just look at the real and imaginary term, or just break this up into cosines and sines. Use the triangle inequality on each part. All right, so if you do that, you can use the mean value theorem with respect to this function here to get that there is some h star between 0 and h, where this is going to be equal to actually 2 pi k cosine 2 pi k h star. And you can also, if you want, use the mean value theorem to this term here, or what you could do is just multiply and divide by 2 pi k. All right. So, so this here is bounded above by 1, of course. And we should know that an absolute value sine x over x for any x is bounded above by 1. So this gives us 2 pi k, 2 pi k. So it's less than or equal to 4 pi k. And I actually want really an estimate for this whole thing here that I'm going to circle. Okay. Well, there's really not much subtle you can do with the minus 2 pi I k. Just use triangle inequality and take the absolute value of that. And that gives us 4 pi k plus 2 pi k, just 6 pi k. Okay. Not a super subtle estimate, but it is independent of h, and that's what's really important. Okay, so what I'm going to do now is fix epsilon. I'm going to fix n where this is true. The terms in absolute value of where absolute value of k are bigger than n, that sum is going to be less than epsilon over 6. I can fix n where this is true because I'm assuming that this sum here when n equals 1 is finite. And the 6 pi is just to get everything ultimately to add up to epsilon. All right. Okay. So I break my sum up, the original sum I need to estimate in terms of absolute value of k bigger than n, absolute value of k less than or equal to n. Okay. As I mentioned, this whole thing here is less than or equal to 6 pi absolute value of k. So let's plug that in. Make that 6 look a little better. Okay. So you plug that in, you get 6 pi absolute value of k, absolute value of ck, plus this sum here. And this sum is less than epsilon over 2. So now we need to estimate this sum here. What's probably the easiest thing to do is take the limb sup as h goes to 0 of both sides now. N is independent of h, so we can bring in the limb sup inside this finite sum. And we would see that the limb sup as h goes to 0, this whole thing here that I'm circling is going to be 0. Okay. And let's actually see that real quick. So you can just recognize this as a derivative of e to the 2 pi I k x at 0. This whole, this right here, and that's going to be 2 pi I k, and hence this limit is 0. Or you can break this up into real and imaginary parts. And again, recognize each term as a derivative, or use L'Hopital's rule, whichever you want to do. This is going to go to 0. This is going to go to 2 pi k. So this whole thing equals 0. So if you don't want to take limp soups, and really there's no need to, let's just do some epsilon delta mumbo jumbo. All right, so pick delta where absolute value of h is less than delta means that this whole thing here is less than epsilon over 2 times this sum. So I'm going to assume that at least one of the CKs, k from minus n to n, is not 0. If it is, then we're already done because, well, this sum here, let's get rid of everything here. Now, if all the CKs are 0 from k equals minus n to n, then obviously this sum here that we need to estimate equals 0. Okay. So let's assume that not all the CKs are 0, and hence this sum here is not 0. Okay. So what does that mean? Well, absolute value of h less than delta implies that this whole thing here is less than or equal to epsilon over 2 times this sum here. This whole term here is less than epsilon over 2 times the sum. So it adds up to epsilon, and that finishes the case n equals 1. Now let's assume the statement is true for n minus 1 and assume that this sum is less than infinity. So certainly I can replace n with n minus 1 and then the sum is less than infinity. That's fairly obvious. Okay. So we can use the n minus 1 assumption. Right? So let's write that down. The n minus 1 derivative of f is 2 pi I k to the n minus 1 ck times this complex exponential. Okay. Now let's call this whole thing here that I'm circling ck tilde. Okay. Now it's pretty clear that modulo absolute value of k ck tilde converges. Well, because multiply by, except for the 2 pi, an absolute value, except for the 2 pi to the n minus 1, absolute value of ck, absolute value of ck tilde is absolute value of k to the minus n. And we're assuming that converges. Okay. So that means the nth derivative, well, let's just use the n. Let's just use the n equals 1 case. Okay. So we'd use the n equals 1 case. We get that the derivative of the n minus 1 derivative is 2 pi I k ck tilde. Well, ck tilde is 2 pi I k to the n minus 1 ck. So that gives us 2 pi I k to the n times complex exponential, and that finishes the proof. All right. So yeah, like I said, it's a not too bad of a proof. Right. So right. So let me discuss a really interesting related proposition. Right? And that is, if I have a function that has n continuous derivatives on 0 to 1, and by a derivative at 0, I mean a right-hand derivative, and by a derivative at 1, I mean a left-hand derivative. And let's assume that the derivatives from 0 to n minus 1 satisfies this condition here. So in particular, f of 0 is f of 1. then the Fourier coefficient is given by this formula here. And what's the main point here? And I should say we have to assume k is not equal to 0. So what's the point here? The point here is, well, the nth derivative is assumed to be continuous on 0 to 1, so it's obviously an L1. And if the Fourier coefficient of any function is an L1, or sorry, if the of any function is an L1, then its Fourier coefficient is trivially bounded in absolute value by the L1 norm on 0 to 1 of that function. You just take the Fourier coefficient, smash in absolute values. So the point is, in absolute value, what I'm circling is obviously bounded. So we're saying that the Fourier coefficients decay like the power, like k to the power minus n, as k goes to plus or minus infinity. All right, so you can, I should mention, you can loosen this condition here a little bit. And in particular, you can loosen it to read that f has n minus 1 continuous derivatives on 0 to 1. And the n minus 1 derivative is absolutely continuous on 0 to 1. And the reason you can do that is basically this is going to be a game of doing n integration by parts. And if you assume that, then you can do n integration by parts. Particularly, you can do integration by parts for the nth. You can do the very last step that we're going to go through. There's no way to, as we'll see in the proof, there's no way to relax this condition here. But anyway. So as I said, the proof is just going to be integration by parts. Let's more carefully do this by induction. So I do one integration by parts, and I'm going to set this to be my u. Okay. And I'm going to set this here to be my dv. All right, so I get uv is going to be either minus 2 pi I kx over minus 2 pi I k. And if you don't like that, just break it up into the real and imaginary parts, do the integration. I mean, in general, if you really don't like doing this with complex valued functions, just break everything up into the real and imaginary part. Is kind of a pain, but if you really want to, you can do that. But anyway, so it's uv minus integral v du. And the whole point is as simple as when you get v, you get a k in the bottom. Okay. So now we're assuming f of 1 is f of 0. Obviously, e to the minus pi I k times 1 is 1. Same thing, plug in 0. So this term here becomes f of 1 minus f of 0 over minus 2 pi I k, which is obviously 0. Minuses here cancel, and we can keep playing this game here. More rigorously, let's assume that the statement is true for n minus 1, so that the k Fourier coefficient is given by this integral here. Okay. Now I can do integration by parts one more time, same thing. This here is my u. It's fine. And this here is my dv. Okay, so integrate to get v. Du is going to be fn of x dx, the nth derivative. Again, by assumption, this here vanishes, all right? Because by assumption, particularly when L equals n minus 1, these two are the same. Okay, so this vanishes, and you're left with this here, should be a bracket, all right? And, well, that gives me exactly the formula I wanted. All right. So one interesting corollary is the following, just kind of combining the two results that we had. And this is more of a theoretical, very general result. In practice, it's a little too stringent to be applied. So actually, before I state this corollary, this proposition is actually extremely important in analysis. Let me get rid of all these comments. It's a bit messy. And this is a theme that is often repeated in analysis, and that theme is there's a trade-off between the smoothness of a function and the decay of its Fourier coefficients, or the decay of the Fourier transform. And sorry, I should say this smoothness of a function and the vanishing of either the function and its derivatives at 0 to 1, or in the case of Fourier transform, vanishing at plus or minus infinity. Okay. The trade-off between that and the decay of the Fourier transform of the Fourier coefficients. And that's exactly what this proposition says. If we have both, then we have decay at infinity behaving like k to the minus n. Okay, so if f is as in the previous proposition, and if f is this infinite sum here, and if this infinite sum in modulus is finite, then we can differentiate f n times by differentiating the Fourier series term-wise n times. Okay, so I should mention implicit here is that this series here and this series here are both absolutely and uniformly convergent for all x. And that really comes from this condition here that I'm circling. Why? Because if this is true, sorry, I went back a little too far. If this is going to be true, then you can multiply both sides by k to the n if k is not equal to 0, and then you get k to the n in modulus f hat of k, when you sum that up, converges. So in particular, the Fourier coefficients are certainly little L1. And you also get that this here, by a Weierstrass M-test, converges uniformly. Okay, so what is the proof? The proof, I basically told you the proof already. You just plug in for what we, so you take the first result that we had. We want to check that this sums to something finite. You take what we just proved a moment ago, plug it in. And, right, so this is for k not equal to 0. I mean, when k equals 0, there's nothing, we don't care. That's just 0 in this sum here. Okay, and well, the n's cancel, and we're assuming this is finite, so. Okay, so as I said, this is a fairly stringent condition, but it's not unreasonable. And it's not unreasonable because certainly, as I mentioned, these Fourier, f to the n is bounded if it's continuous on 0 to 1. So it's Fourier, so f to the n is obviously in L1. And whenever you have an L1 function, the Fourier coefficients always converge to 0 as k goes to plus or minus infinity. You really don't know how, but it always converges to 0. And this is the Riemann-Lebesgue lemma. And interestingly enough, you prove this essentially by integration by parts. You approximate f by a nice function in L1, and you apply integration by parts to that nice L1 function. Okay. Right. So typically, because of that, you would expect faster decay. You would expect maybe, at least k to the minus 1 decay if you're going to employ integration by parts. But in general, you really don't know how fast Fourier coefficients go to 0. And the best you can say is this Riemann-Lebesgue. And this was actually a prelim problem a few years back. Okay. Okay, so what is very practically useful, and we'll illustrate all this through an example in the next lecture, is if f is as in the previous proposition, then the Fourier series of the nth derivative, regardless of whether it converges to the nth derivative and regardless of whether it converges to anything, is obtained by n termwise differentiations of the Fourier series of f of x. So it's a mouthful, but what we're doing is, well, let's look at the Fourier series of the nth derivative of f. That's by definition this infinite sum here. Okay, we have a formula for the nth derivative of, the Fourier coefficient of the nth derivative. And that is exactly this here, when k is not equal to 0. Okay, we'll take care of k equals 0 in a second. And obviously, this is what you get when you differentiate this n times. You just pick up a 2 pi I k to the n. Okay. So what about k equals 0? Well, what about it? Well, there's nothing subtle going on here. The exponential goes away, so we're just taking the integral 0,1 of the nth derivative. That's going to be just fundamental theorem of calculus. F to the n minus 1 of 1 minus f to the n minus 1 of 0. And we're assuming that's 0. That's part of our assumption here. Okay, that particularly when L equals n minus 1, this is going to be 0. Or rather, you subtract, you get 0. Okay. So in particular, right, when k equals 0, the Fourier coefficient of the nth derivative is just 0, so that this is true for all k. Okay. So really, in practice, this is what's really useful and really powerful. And what you do in practice is you basically differentiate term-wise a Fourier series, and then you try and use some general theorems on convergence of Fourier series to show that the term-wise differentiated Fourier series converges, particularly converges to what you want. And that really, in my opinion, stresses the need for a very general convergence theorem for Fourier series. And we'll, and not the next one, but the lecture afterwards, we'll do just that based on where we ended off in the last video, which is exactly right here. Remember, this is the partial Fourier series for f, ending at n, where n is a positive integer. So what I want to do in the next video is really illustrate everything I did here through an example. And I want to go over, how to typically, not a very general statement, but more typically how to kind of by scratch prove that a typical Fourier series converges to something, point-wise and uniformly, when you can't just smash in absolute values and use the virus test M test. And we'll talk about what's called the Dirichlet test. It's a very nice little innocent looking test, but it's extremely powerful in the study of Fourier series. And then after that, we'll get back to looking at this integral here and how to prove that when n goes to infinity, this is going to be 0. All right, so it's a good time to end. Again, any questions, concerns, comments, please email me or ask them in the office hours on Zoom, and I'll make a small 2 or 3 question homework set very soon. So not everything I say is homework will be collected, though it's probably good to do everything I say is homework. Anyway, so long, farewell, and expect a new video pretty soon. Take care. Bye-bye.